Hi everyone, welcome back to Labyrinth Academy. I'm Liyanaarachchi, your physics tutor. Before we start 6C3 magnetic forces, make sure you have seen 6C1 magnetic field and 6C2 electric motors. Those give the field ideas and how currents feel forces. Today, we'll focus exactly on how magnetic fields exert forces on current carrying conductors and moving charges. The formulas you must know, how to predict direction, and short work ideas you will meet in exams. Let's get started. Let's begin with the wire carrying current inside a magnetic field. The force acts on it because the moving charges in the wire are being pushed by the field. The size of the force is given by the formula F equals BIL sine theta. In here, B is a magnetic field, I is a current flowing through the wire, L is the length of the wire within the field, and theta is the angle between the current and the lines of the field. F is maximum when at 90 degrees, and then F equals BIL. F is 0 when at 0 degrees, that is in parallel. This is the motor effect, the principle behind motors and loudspeakers. Since we have already studied Fleming's left-hand rule and the basic motor principle, I won't repeat the diagrams here. Now let's move from a current carrying wire to a single charge particle like an electron. The formula is very similar. So the magnetic force on a moving charge is given by F equals BQV sine theta. Here, B is a magnetic field, Q is a charge on the particle, V is the particle's velocity, and theta is the angle between the velocity and the magnetic field lines. To find the direction of the force, we can use Fleming's left-hand rule. For a positive charge, the direction indicated by the rule is the actual force direction. For a negative charge, like an electron, the force is opposite to the direction given by the rule. In the rule, the thumb represents the direction of the force, the first finger represents the magnetic field, and the second finger represents the velocity of the particle. The force is always perpendicular to both the velocity and the field. This has important circumstances. Since the force is sideways, it does not change the particle's speed, only its direction changes. The magnitude of the force depends on theta. It is maximum when theta equals 90 degrees, that is, velocity is perpendicular to the field. Then the particle moves in a circle. It is 0 when theta equals 0 degrees, that is, velocity is parallel to the field. Then the particle moves in a straight line. When intermediate angles, that is, theta is in between 0 and 90 degrees, then the particle moves in a helix along the field lines. So, the particle speed stays constant, the path curves, and the force changes in magnitude depending on theta. Now let's consider a charged particle moving perpendicular to a magnetic field so that it moves in a circular path. For any charge, the magnetic force always acts towards the center of the circle, so it acts as a centripetal force. The velocity of the particle is always tangent to the circle. The force is perpendicular to this velocity, so the speed stays constant, only the direction changes. In our diagram, the magnetic field is directed into the paper and the positive particle moves anticlockwise along the circular path. For a negative particle like an electron, the magnitude of the force is the same, but the direction of rotation is opposite. That is, if the positive particle moves anticlockwise, the negative particle moves clockwise along the circle. Again, the force is always radial towards the center, that is centripetal, and the velocity is always tangent to the path. So, the speed remains constant, only the direction of motion changes. This shows clearly that the magnetic force does not do work on the particle. It only changes the direction. And The rotation just depends on the sign of the charge. Let's talk about the radius of a charged particle moving in a magnetic field. First, if you know the particle's velocity perpendicular to the magnetic field, the radius of the circular path is R equals mv over qb. Here, m is the mass of the particle, v is its speed perpendicular to the field, q is the charge of the particle, and b is the magnetic field strength. The magnetic force acts towards the center of the circle, that is centripetal. The velocity is tangent and the speed stays constant. Sometimes we don't know the velocity, but we know the kinetic energy of the particle, which is given by k equals half mv squared. Solving for and substituting into the radius formula gives R equals square root 2km over qb. Here, K is a kinetic energy, M is a mass, Q is a charge, and B is a magnetic field strength. In practical situations, a particle is often accelerated through a potential difference. Its kinetic energy K equals QV. Substituting this into the previous formula gives R equals square root 2mv over qb squared. Here, V is the accelerating potential, M is a mass, Q is a charge, and B is a magnetic field. This shows clearly that the radius increases with the mass and energy and decreases with the charge and magnetic field strength. Using both formulas helps students connect the physical motion to real situations like electrons accelerated in a lab or ions spiraling along a magnetic field. Now, if the velocity of the charged particle is parallel to the magnetic field, that is, theta equals 0 degrees, then the magnetic force is 0 and the particle just moves in a straight line along the field. But if the velocity makes an angle between 0 degrees and 90 degrees with the magnetic field, then we can think of the velocity as having two parts. A parallel part, which takes the particle move forward, and a perpendicular part, which makes the particle circle around. When these two combine, the particle follows a helical path. In space, charged particles from the sun spiral along the Earth's magnetic field lines in exactly this way. This spiral in motion is what gives rise to the beautiful auroras, the northern and southern lights. One important application of charged particles in a magnetic field is a mass spectrometer. In a mass spectrometer, ions are accelerated through a potential difference and then enter a magnetic field which makes them move in circular paths. Ions with different mass to charge ratios follow different radii, so they separate naturally according to their mass and charge. By measuring the radius of the path, we can determine the mass to charge ratios of the ions. This allows us to identify isotopes or analyze the composition of a sample accurately. We see how an electron beam is deflected in a magnetic field. When electrons enter a magnetic field, they experience a force perpendicular to both their velocity and the field. This force bends the path of the electron sideways. A simple demonstration using a cathode ray tube shows this deflection clearly. The direction of the deflection depends on the sign of the charge and the orientation of the magnetic field. This experiment illustrates directly the basic principle of the magnetic force on a moving charge. To finish, let's connect everything. For wires, magnetic force gives the motor effect. For particles, it provides centripetal motion and creates circular spiral paths. Applications include cathode ray tubes, mass spectrometers, cyclotron, and motors. And always remember, the magnetic force is at right angles. It changes direction but not speed. That's the essence of this lesson. In the next video, we'll practice some checkpoint questions to strengthen your understanding and to supervising. If you found this video helpful, don't forget to like the video, subscribe to Labyrinth Academy, and check out other lessons and our educational documentaries. See you next time.